So we've got this new function, logarithms, to use in our little tool chest of functions. But of course we want to do calculus on it. That's part of the main game of this particular course. So let's see how we differentiate it. Now, proving this is a little bit easier once we know how to differentiate exponentials. So I might actually wait to prove it till we've looked at the exponentials. It turns out this though. So if you want to differentiate the log of a function, basically you just differentiate the function that goes on the top of the fraction and the original function goes on the bottom of the fraction. So derivative over the function. That's if it's a natural log. If it's not a natural log, you still do exactly the same thing, but on the bottom of the fraction you get the natural log of a. That's basically due to the change of base rule. So that's why you end up with the log of the base on the bottom of the fraction. But other than that, it's exactly the same, derivative on function. So, here's a tricky one. Y is the log of 3x plus 5. So we have to differentiate 3x plus 5. That would be 3. Over the original function itself, so 3 on 3x plus 5. Log of x cubed, well, there's actually a couple of ways we could do this. I could say, well, derivative on the function 3x squared on x cubed, which of course then cancels down to be 3 on x. The other way I could do it is I could use a log law and say, let's bring that 3 to the front of the log and then differentiate the log x. Differentiate log x, you get 1 on x, 3 times that, 3 on x. Just a matter of preference, I guess, which way you do that. And I mean, neither's really too difficult. So. The log of log x. So derivative on function. So what are we differentiating? It's the log of a function. That function is log x. So the derivative, we're differentiating the log function. So we get the derivative, 1 on x, over the original function, log x. So you get 1 on x log x as the final answer. Now something like this. I could look at it this way and say, well, there's the function x plus 3, x plus 2. And go, okay, derivative. Well, I'm going to have to use a product rule to do the differentiation there. Write down the first, div the second, plus write down the second, div the first, over the original function, and tidy that up. I could do it that way. Or I could use my log laws and separate them into 2 logs, because multiplication, remember, we add the logs. And differentiate log of x plus 3, well, that's just 1 on x plus 3. Differentiate log of x plus 2, that's just 1 on x plus 2. Now that's an answer for the derivative. Okay, I haven't combined the two together. I guess it all really depends what you're going to go and use the derivative for. Now if you wanted to find stationary points, well then you'd need to turn that all into one fraction. But if you were just substituting into the derivative, then that's a perfectly fine answer to do that for, rather than mucking around with the algebraic fractions. If we did do algebraic fractions, then we'd go, common denominator, x plus 3, x plus 2. And you can see we're going to end up with exactly the same, because now on the top of the fraction, I've got 1 times x plus 2 and 1 times x plus 3, and we get the same answer. So to say, it really depends what you're using the derivative to do as to whether you would do it the second way or not. Similarly, with division, and this one here, if I don't split it up, really becomes fun, because to differentiate a function, I got to use the quotient rule. So square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom, over the original function itself, x plus 5 and x plus 2. I might invert and multiply, make it a little bit easier there. And tidying the top, we get negative 3. With the x plus 2, we'll cancel with the x plus 2 squared. And we end up with minus 3 on x plus 2, x plus 5. If I use my log laws, I just got 2 nice log functions there to differentiate. 1 on x plus 5 minus 1 on x plus 2. Bingo, there's the derivative. Now, again, depending on what you're going to do with it, but if we combined it all into 1 and then tidy the top up, I still think possibly the second way is a bit easier than a lot of places to make algebraic mistakes in the first one. Yeah. But again, matter of preference. Well, here's one that's not a natural log, but what I said was it doesn't matter. We still do it the same way. derivative on the function, but we multiply the denominator by the log of the original base. So we get the log of 10. It's usually easier to write the log as the second term, because you can see if I forgot my parentheses there, I could easily read that as the log of 106x or something like that. So we tend to put the log 10 as the second part. Makes it a little bit clearer. All right. Wow. Lots of fun there. So 12b and 12c. Of course, part of this exercise will be not only just differentiating, but then all the sorts of questions that we saw and used differentiation for: curve sketching, finding your stationary points, your turning points, inflection points. But now with the log function as well. Hours of fun for the whole family.